So up until today, we've been looking at circular motion that was uniform. Okay, that meant that the speed of the object moving in the circle is staying the same all the time. Okay, so basically horizontal circular motion. Okay, that's uniform circular motion. Vertical circular motion is not uniform. Okay, just watch the motion of the tape here. Okay, it's staying in the circle, but what's happening to its speed? Slows down at the top, speeds up at the bottom, right? Because now gravity plays a role. Okay, in any vertical circular motion, gravity plays a role, which means the experience of someone in vertical circular motion is going to be considerably different than someone experiencing horizontal circular motion. So when you're on the gravitron, that's uniform. That's the I just totally blanked on that. I want to say universal, but I knew it wasn't right. Uniform circular motion, okay? Because the velocity is constant. So your experience is, I feel this way, and I feel this way all the time. But if you're in vertical circular motion, your experience changes depending on where in the circle you are. Okay? Near the top, how are you going to feel, do you think, compared to the bottom? Lighter, yeah. In fact, at the top, depending on whether you're on the inside of the circle or the outside of the circle, you could even feel weightless. And depending on how fast you're moving. All right? Anyone ever gone over like a kind of a top of a hill on a road, but you go over it like 100 kilometers an hour, and you get that feeling of, your insides like coming up into your throat? Okay? That's because you've just gone over the top of a vertical circle. And gravity is trying to keep you in the circle, but your inertia wants you to go, not up, but straight. It wants you to leave the circle, right? So, slightly up. It basically wants you to become a projectile. In fact, if you went fast enough, you would become a projectile. Okay? No, I'm not suggesting, in fact, I'm telling you not to do this, but I've seen somebody do it. I've seen somebody hit that big speed bump out there. At speed. It did not end well. Okay, that's why I'm telling you should never do it. Not only is it not safe, but it ended very, very poorly. Like, there was this metallic lump that stayed behind the car. What's it called? Transmission. Okay, so yeah, you kind of need that. It's kind of important. Okay, because yeah, they hit the bump and it's just like a vertical circle, the top of a vertical circle. Okay, and they were going fast enough that they launched off of it. Now, I'm not saying it was like a Dukes of Hazzard over the river kind of launch, but it was enough that they got air. And then when they came down, okay, gravity made them, that's why all projectiles follow that arc. It's because they're all kind of a vertical circle caused by gravity. And so that thing came slamming down onto the ground, okay? The suspension couldn't handle it, so it bottomed out. And, there's lots of things that kind of hang out on the bottom of the car that normally don't touch the ground. And when they do, they generally are not secured well enough to stay on the car anymore. So, yeah, you definitely don't want to do that. But that's vertical circle. The people inside the car would have felt, well, before they crashed down onto the ground, weightless. Yeah, there would have been a period of apparent weightlessness for them. Okay? In fact, this is how NASA's Vomit Comet works. The plane that they use to film all the zero gravity scenes in science fiction movies. Okay? That's how it works. It just flies over the top of a vertical circle. It just flies in this pattern. Okay? Once it goes over the top of the vertical circle, people feel weightless, okay, for quite a while. And then when the plane starts to pull out of the dive, okay, the gravity will return. And in fact, they'll feel twice normal gravity for a little while as the plane pulls out of the dive. Okay? And then it'll accelerate up again, and then when it gets over the top, they'll feel weightless for another 30 seconds, and so on and so on. Okay? So vertical circles can do some strange things. Now, that's going over the top. What if you're on the inside of a loop, like on a roller coaster? Okay? So instead of being on top of the circle up here, you are here, under the circle. How do you feel there? The answer is it depends. It depends how fast you're going. Okay? If you're going just fast enough to stay in the loop, okay, because there is a certain minimum speed required. If you don't go fast enough, you fall. Okay, I'll show you a video about that. I have lots of videos for this. Okay, if you don't go fast enough, you fall out of the loop. If you go just fast enough to stay in the loop, you don't push on the track. And so the track doesn't push back. How do you feel? You feel apparent weightlessness. You're not actually weightless, but you feel like you are. Okay, because your normal force is 0. Okay? If you go faster than the minimum speed, you can actually feel heavier than normal. Right? If you go on like the roller coaster at Callaway Park, or if you've rode the Mindbender at West Edmonton Mall, the G-force at the top of the loops on the Mindbender is over 3 Gs. Okay? G-force at the bottom of the loops is over 4. Okay? Because again, gravity is working for you and against you on the bottom, for you on the top. Okay? But you actually feel heavier than normal all the way through the loop. You can see it when you watch people go through, because if they're not ready, their chins are pinned to their chest through the whole loop, because they don't realize just how heavy their head is at 3 to 4 Gs. Okay? So they're like, yeah, and they're just going through the loop, and they just don't realize. Like if you brace yourself, okay, you can be ready for it. Right? But it is a fair amount of bracing, and your head gets heavy. Okay? I know the one time where we went there, and we were the only people in the park. Some of the students rode the Mindbender from one maintenance check to the next. Okay, which I can't remember how long it was, like an hour. Okay, and the next day, they said when I got out of bed, I had to look to one side. I basically had to turn my whole body. My neck was so sore. Okay, from holding up their head. Okay, at that G-force for so long. Okay. All right, so is that kind of making sense, this idea? Okay, and then we said, like, if you're here at the bottom of a loop, your inertia wants you to go out of the loop, but the loop pushes on you, and so you actually feel heaviest here at the bottom of the loop. Okay, that's when most people would black out. Okay, is at the bottom. Okay, so this still works like what we talked about in Unit 2. FC is still our net force, okay? Which is why we can calculate it using the forces acting into the circle minus the forces acting out of the circle, because now we actually do have some forces that can act out of the circle. Okay? We can have gravity that can act out if you're on the bottom, or in if you're on the top. Okay? It changes, right? And gravity always acts down, but in reference to the circle, that could be in or out, depending on where you are. Okay? So we can calculate FC by going forces in minus forces out, because that's the vector sum of all forces. Okay? Centripetal force is in, so we add all the forces that are in and subtract all the forces that are out. Okay? We'll always get the net force. Now I make it sound like there's lots and lots of forces. Okay? There's like 2. Okay? So it's not something we really have to worry about too much. Okay? But we just have to remember forces in minus forces out, and we should get a positive number. If we don't, we're in trouble, because that means there's more force out than in, and we're flying out. All right. So, to do this trick is tough. Okay? If you're on a motorcycle or in a car, it's not too bad because you can move fast enough. But to actually go through a vertical circle and stay in it requires you to be going reasonably fast, even for a small circle, right? Because you have to achieve that minimum speed where your inertia balances the desire of gravity to pull you back to Earth, okay? The real trick, with a car, it's not too bad. You just build up a lot of speed and zip through the loop. Do you think you could run one? Oh, I have it on YouTube. Sorry, it's on
running a small circle and some bolt.
Okay, so you can actually run it. Not easily. Okay, like I mean, this guy's practiced a lot and chickened out on it about a half a dozen times, but I don't think I could have ever gotten to the point where I'd be comfortable running upside down. Okay. So, I mean, you can do it, but you have to achieve this minimum speed. Okay, so let me show you how some other people thought it might be fun to do it. All right, so yeah, you got to get to that minimum speed. And you have to achieve that, otherwise you're not gonna be able to stay in the loop. Kind of like how many people have seen the Simpsons movie? Okay, where Homer has to circle the ball of death. Okay, we'll watch that one too. To get through a vertical circle by driving straight up it like that, you'd never be able to do it. Okay, but people do that trick all the time. They just gain speed by kind of going around and around in a horizontal circle for a little while, and then that horizontal circle becomes more and more vertical, and then they make the loop. So totally possible, okay, but you have to achieve that minimum speed. When you're at that minimum speed, you are essentially a projectile. Okay, and what makes a projectile have a projectile arc? Gravity. Okay, that's your force in. Okay, when you're at the top, going just fast enough. Okay, so remember we said Fc equals forces in minus forces out. Okay, so you'd have mv squared over r equals m times g. Okay, if you were at just the minimum speed. What if you were going faster than you had to? Then you're going to have some normal force as well, because your inertia is going to make you push on the track, and the track's going to push back. So you'll have gravity and normal force. Okay? Now remember, our formula said forces, plural, in minus forces, plural, out. So it would actually be plus Fn. Are there any forces out when you're there? There aren't. Okay, not in that situation. There are no forces acting out. Nothing's trying to throw you out of the loop. Okay, because remember, your inertia is not a force. Okay, so you'd have that. You'd have to know what Fn is. A question like this might ask, if you're going this fast and the radius is this much and your mass is X many kilograms, what's your apparent weight? Okay, this is apparent weight. You might want to write that down because it comes up all the time in this unit. If a question is asking for apparent weight or gives you apparent weight, normal force is apparent weight. It is how heavy you feel, not how heavy you are. Okay. So does this mean if you were going on a vertical circle, obviously there are times where you would feel weightless. Does it mean you could possibly leave a vertical circle? Yeah, you could leave at least the initial radius of the circle you were traveling in. You would simply become part of a larger radius vertical circle, which would be your projectile arc. Okay? But there's actually something that they do, well they did, I don't know if they still do it. Cirque du Soleil changes all the time. But years ago when it was Cusa, Cirque du Soleil Cusa, they had this double wheel of death. And it was they looked like hamster wheels, okay? And they were attached to a pivot point. So there was a hamster wheel, 2 hamster wheels and a pivot point, and the whole apparatus rotated, okay? And I'll show you a video of that later. I don't know if we'll get to it today, but of these guys that, and when they're in it and on top of it, what happens to them? Like they can actually be thrown upwards, and then they actually come back down onto it and catch it later, simply because of all these laws that we're going to look at. Okay, so if we're looking at a vertical circle, this is what it looks like from kind of a free body diagram type of idea. If I'm at the bottom of the loop, okay, so I'm down here, what I'm seeing is that gravity pulls me down. So gravity is acting in or out? Out. Okay, so when you're at the bottom of a vertical circle, gravity is out. Normal force is in. Now the normal force is greatest at the bottom of a circle, because the normal force has to counteract not only gravity, but also your inertia. Yeah, well, mass is a measure of your inertia, so yeah. Okay, so you're trying to leave the circle prevents it, plus gravity is pulling down. That's where you feel heaviest. It's where your apparent weight or normal force is the greatest. The bottom of a loop is where you're gonna feel the heaviest. Okay, next time you ride a roller coaster and you go through a loop, you'll notice, okay? Because when you're at the bottom of that loop, you just feel, like crushed, okay, at the bottom. Right? At the top, you also feel a bit thin, but not as crushed as you do at the bottom. Now, the sides are not a point that we ever work with, because we've already done problems that are like the side of a vertical circle. And that's because gravity is perpendicular to, or tangent to the circle on the sides. It means it doesn't play a part on the sides. Okay? Only the normal force of the circle, or the tension in the rope, or whatever, and it's just like a uniform circular motion question for the sides, so we never do the sides. Okay? If we're on the inside of a vertical circle, then as we said before, gravity is pulling into the circle, and normal force is pushing into the circle. If you're on the outside, normal force changes direction. Normal force acts out because you're pushing down on the circle, and the circle has to now push up because you're on the outside of it. But this is where you can feel the apparent weightlessness. If you go fast enough, you will lose contact with the circle. And if you can't touch the circle can't what? It can't push on you, which means you feel weightless. You're not weightless, but you feel that. Okay? Everyone all right with that idea? Okay? Those are the only three situations we're going to deal with for vertical circles. Bottom on the inside, top on the inside, top on the outside. Okay? Why don't we deal with bottom on the outside? You can't. Okay? You cannot have a situation where you're on the bottom on the outside. Okay? If this is something that I'm whirling around on a string, okay, it's not, when it's on the bottom, it's not on the outside. It's on the inside. It's being pulled in by the string. Okay? But if I built a roller coaster where the cart was like this, could I then have that situation? Could that be bottom on the outside?
That just can be the same thing as top on the outside, just before the force.
Kind of. Here's the problem with building a roller coaster like that. It would kill everybody on it. And not because they fly off the track. Okay? A roller coaster is built so there's a set of wheels on either side of the pipe so they don't come off the track. But if I do this, my inertia wants to leave the circle. Gravity wants to leave the circle. Where does all my blood go? Straight to your head. Okay? When you're here on the inside, the blood rushes away from your head and you lose consciousness and you black out. What happens here is what's called a red out. And it's because you will get like a massive aneurysm. The blood vessels in your brain could break because of the overpressure of blood. Okay? Fighter pilots have to be worried about this. If they go inverted and do this, it can kill them. Okay? Because the force of the blood going to the brain, those tiny little capillaries in the brain and in the eyes and stuff like that, they're not meant to take that kind of force. Okay? Like you can survive blacking out, but you can't survive redding out. Okay? It's what we call negative G forces. The body cannot tolerate negative G's. Okay? Very small amounts for very short periods of time, yes. Sustained negative G's are deadly. Okay. All right. That making some sense?
Just wondering, how does the concept of negative gravity work?
Because you feel, because it's going the opposite way, perceptually. It's not truly negative, it's still forces, but it has to do with the way the blood would go, right? I wouldn't feel heavier in the direction I normally feel heavier down. I would feel heavier in the direction I don't normally feel heavier up, right? My blood would all go to my head. Do that.
So you could just like, if you're doing a handstand and you're upside down, that's negative G's.
It's 1G. It's still 1G. You're
Yeah.
like, you're not, you get dizzy, right? I mean, you can't get a headache if you're hanging upside down for extended range. Some people, that's like a a back therapy. They get the boots, right, and they hook them onto the like chin-up bar, and they just hang, and it can help to loosen your back. Some people say that it's good for sleep. I can't imagine sleeping hanging upside down, but yeah, it's hanging upside down for short periods is okay because it's just 1G. Yeah, blood is going to collect in your head, but it's probably not going to kill you. It's not good for you long term to hang upside down. The body didn't evolve upside down. All right. Making sense so far?
So if you were doing a handstand on an elevator that's going downwards, that would be negative G's?
No, because you feel lighter when it's going downwards.
Oh.
So it wouldn't be as bad. If you're doing a handstand when it was moving upwards, that would be negative G's.
What if you had an elevator accelerating downwards at like 10 meters per second, so like equal greater than gravity, and you were upside down?
Sorry,
How
I'm
would
hearing
that
something else. Is somebody cursing up there? Sorry. Okay, you're in an elevator. It's just weird. I just heard something. I was like,
So would
I
it be
couldn't
like-
hear you over it.
Would it be like the same effect as like low gravity if you were just upside down and the elevator was accelerating downwards faster
Yes.
than gravity?
Yeah. Well, if the elevator is accelerating downwards faster than gravity, you're pinned to the roof.
Yeah, but you're like upside down, so
Still, your feet are pinned to the roof. Yes, it would be. Yeah.
that's cool.
No, it better be a tall elevator or you're in trouble.
What if you did a handstand on a roller coaster?
That would be very unsafe.
Okay.
I don't know what.
But yeah, everything would be reversed. Okay, so if you were upside down on a roller coaster and it was going through its normal thing where people would normally be seated, you'd be in a negative G situation.
So you would read at the top instead?
What's that?
So if you were doing the handstand, you
You'd
would read
black out.
at the top?
No, you'd red out at the bottom.
Oh, okay, no.
Okay. That's everyone's okay with the 3 spots on the vertical circle? Okay, so we're gonna watch the Cirque du Soleil video, and then I think we'll do the zero gravity, the apparent weightlessness thing another day. We'll have to see what kind of time we have. Okay, so what we're gonna be looking at next week is we'll be looking at a bunch of problems to do with FC equals forces in minus forces out. Top of the circle, all we have to do is analyze, okay, which ones are in, which ones are out, and then plug them in and solve for whatever the question is asking us to solve for. So we'll work on that on Monday. Remember that next week you got 2 lab reports due, okay? Tuesday and Friday, I believe. Okay, so make sure you've got, is it Monday and Friday? Okay. So whatever the 2nd and the 6th are, those days, okay? I didn't make anything due on May the 4th because it's Star Wars Day. All right. Yeah, we'll call it a day there, guys.